Everything I handed out last Tuesday, Tuesday, and again on Thursday, if you were here. In addition to that, I've got this lab, right? Determination of molecular weight of an acid. That's the one we're going to be doing a week from today. So if things work out and I can get finished with a review, then we'll spend a few minutes on that to get oriented toward titrations. My guess is that titration is a foreign language to most of you. If it isn't, so much the better. All right. So where we left off, we were just getting ready to look at exam 5 material, chapter 7, review problem number 46. And I can see that is not going to last, so I might as well just get a new one now. Okay. The statement that the lowest energy configuration of an atom is the one having the maximum number of unpaired electrons allowed by the Pauli principle in a particular set of degenerate orbitals is known as. I don't think we mentioned degenerate yet. So let me define that. Degenerate in chemical terms means that all the electrons have exactly the same energy. They're not roughly, well, they of course they have to be the same n. They have to be the same principal quantum number. But degenerate orbitals are ones that go even further than that. All right, so if we have, well, let's just use a real example. Let's say n equals 3. Then L could either be what? 0, 1, or 2. Well, let's say we pick 2. Right. So how many m sub L's can you have? Well, you can have a, let's pick 1. 1 would be a better example. Let's use 1. We can have -1, 0, and +1. Okay. So you can have, and for each one of these, right, our m sub s's can either be spin up or spin down. Either way. Okay. When we say degenerate orbitals, we're down to this level where these are exactly the same energy. If we have orbitals that are say we have 0s and 2s, they'll be a little bit adjusted away from each other, a little bit difference. We're talking about exactly the same energy, and that's why we're down to m sub L, because these orbitals are exactly the same energy, and those are called degenerate. So let's get back to the question. What rule or principle says that when we have more than one electron going into these orbitals, and remember this is a shell subshell orbital. So when we have more than one electron going into the this level, these orbitals, what do they prefer? They prefer to go in separate on these separate individual orbitals like that. If you have 3, then they'll be in separate orbitals. Only if you have 4 or more, you have to start pairing them up. But you don't start pairing them until you've got a single electron in each one of these orbitals. Now that rule is Hund's rule. All right. So that would be B. Hund's rule says whatever that is on the screen. All right. 47. Let's see. An element has the electron configuration. We're going to use the shorthand version here. It's got krypton. I like to write the Z number in there for 36. They don't always do that, but I prefer it. 5s2, and then 4d10 and 5p2, correct? Yep. Okay. The element is what? Where are you going to find this element in the periodic table? So if we look at a schematic of a rough approximation of the periodic table, it goes over like this, and then it goes down here, and it goes like that, and it goes up here like this, and it has hydrogen up here by itself. Okay, so remember, these two columns, these groups, are s orbitals. These 6 groups here, right? So we have 1, 2, 3, 4, 5, 6. We have these 6. These are all p orbital filling. The transition metals are d orbitals. And then, of course, the lanthanides and the actinides are both f orbitals. Right? So if we're filling a p orbital, right here, the highest level, highest energy level is p, our element's going to be in here somewhere. All right, so what we have to do is decide where is it in relationship to that zigzag line, I think. First of all, how far over are we? Once we get into the p's, we're only 2 over. But we have to find out 5p. So 5 is the period. So we go down to period 5, which starts at 1, 2, 3, 4, 5, rubidium. And we track across rubidium until we get to the p's, and then we go 1, 2. So that's actually 10 equals 10, 50. Okay, we can check ourselves, right? That's 14, 14 plus 36 is 50. So 10 is on this side, right? In the 5th period. That means it's a metal. Okay. Now, I try not to muddy the waters when I ask questions on the tests. If it's really close to this line, it could be a metalloid. Okay. So if it's right on the line and the metalloid is a choice, that's probably a better choice than metal. Especially if it's on this side. So on that side, you would call it a non-metal, or if it's right on the line on that side, it could be a metalloid. But I avoid that because it's just too confusing. All right. Oh, so the answer is C. All right. 48. All right. An element with the electron configuration xenon, which would be 54. And what else does it have? 6s2, 6s2, 4f14, 4f14, and 5d7. 5d7. I should have erased my thing. It's really faint. But we know that we're past the alkaline metals and alkaline earths. We're past the, let's see, 4F would be probably a lanthanide. Let's see if we're at 6. 1, 2, 3, 4, 5, 6. Yeah. This makes it it's past the lanthanides because 14, right? F, you can have 7 and times 2 electrons each is 14. So we're past that. Now we're into the D's. So if we come across to the D's and we go 1, 2, 3, 4, 5. Oh, wait a minute. We're D's. Excuse me. We're D's. D7. All right. D7 would put it 1, 2, 3, 4, 5, 6, 7. Let's see. Is that 16, 23, 54? Yeah. 77. That's what I thought it was. So that's iridium. 77. What's the question? would belong to which class in the periodic table? Well, it's a transition metal, transition element. Right? It's in that group. And this gives it away. We're filling d orbitals. I just wanted to know which one it was. All right, 49. All alkaline earths have the following number of valence electrons. This is just memorized. Alkaline earths are the second column, right? Those are all s orbitals, and s's can only have 2 electrons, right? But it's in the second one over, so it has to have. It's just got 2. It's only got 2 valence electrons because it's something S2, right? Whatever that is. That's the highest. The highest principal quantum number, and an s orbital is only 2 electrons. That's why we learned early on, right? The alkaline metals are, when they become ions, they're +1s. And the alkaline earths are +2, always. Just for that simple reason. Okay, 50. Try that again. Ti, which is titanium. Yeah, titanium. Titanium has blank in its d orbitals. How many electrons? You look at the answers, you can tell we're looking for how many electrons in the d orbital. Okay, so titanium has 22. It's the first transition metal row, which happens to be 1, 2, 3, 4. It's the 4th period, so it's going to be 3D. It's 3D something. So once we get to that point, we come over 2 places, and it should have 2 electrons in the d orbital. Okay. All right. Moving right along. 52. Fe. Iron, yeah. Ferrum. Iron has a blank number of electrons, are unpaired in its d orbitals. Okay, so this takes a little bit more detective work. Iron has 26 electrons. And let's see, we can put argon in here at 18 is the core. So that leaves us 8 more, doesn't it? Okay, so once we move down to the 4th period, we have 4s, 2. Then we move into 3D. Let's see, 2, that's 20. So we have 6 electrons here. Okay. But when we're talking about paired and unpaired, we're going to a level below that. Right? SPD, 0, 1, 2. So this could have -2, -1, 0, +1, and +2. So it can have 5 orbitals at that shell level. Okay, if it's got 6, then it's going to go in like this: 1, 2, 3, 4, 5, 6. And I'm looking to be sure. I think that's right. So the question is unpaired. So we're saying it has 4 unpaired electrons. Now there are a couple of places in the periodic table, in the d orbital fillings and the p orbital fillings, where you get anomalies. Right? This is not one of them. You draw it just like you think it should be. 1, 2, 3, 4, 5, 6. So I only point those out if we come across them. 52, who's next? Oh, 53. Okay. Let's see. Nitrogen has 5 valence electrons. Consider the following electron arrangements for the next 2 questions. All right. We're going to have both questions. All right. So let's look at 53 first. All right. Which represents the ground state for nitrogen? Remember the ground state. That is, all the electrons are in their lowest possible energy under conditions that are normal, standard temperature and pressure. You can have ground states that are higher, but the environment has to be different. So when we say ground state, we don't qualify it. We mean like room conditions. So nitrogen has 7 electrons. So we start off 1s2, 2s2, 2p. Let's see, the 4, we need 3. Okay, but they're giving us orbitals that we have to deal with, right? These guys, there's only one choice, right? You would do like this, like that. And then these p's have 3 possibilities, and we have 1, 2, 3. Okay. So paired, paired, 3 unpaired. Oh, they're skipping this one right here, right, in that chart. They just skipped over the 1s. We're talking about the valence shell. So that means these need to be paired. That's A, D, or E. And then we look at these, we have to have 3 unpaired. Well, it's got to be A. Right? A is the only one that matches that. Okay, 54. What if we form the negative ion from 54? What does that do? You have to add an electron, right? That's added 1 electron. Because you have 7 protons, now you have 8 electrons. Okay, so 2, 4, 5, 6, 7, 8. Now we have that one paired. And let me see, let me scroll back up. We got to have, let's see, it looks like E. E has this one paired, that one paired, and these unpaired. So E should be the correct answer for 54. Alrighty. 55. Now, if nobody stops me, I assume that it's all making sense and it's sinking in. In which group do all the elements have the same number of valence electrons? So remember, valence electrons, we count N equals something. As long as N is the same, those are valence electrons. So let's see. The easiest way to tell if we have the same number of valence electrons is to find the 3 in the group that are in the same vertical, in the same group. They would have the same number of valence electrons. So phosphorus, sulfur, chlorine. Well, we know chlorine's not. Chlorine's a halogen and phosphorus and sulfur aren't. So A's out. Right, A's out. How about B? Let's see, silver, cadmium, argon. No, that's the only noble gas in there. Can't be. How about C? Sodium, calcium, barium. Calcium and barium are both alkaline earths, but sodium is an alkaline metal. Right? That can't be. Phosphorus, arsenic, and selenium. Let's see. Phosphorus is a pnictogen, arsenic's a pnictogen, selenium is a chalcogen. That can't be either. Right? So none of them. None of them have the same number of valence electrons. Let's see. Whoops. Skip one. We get 58 and 59 together. All right. Of the following elements, which has occupied d orbitals in its ground state neutral atoms? Occupied d orbitals. Doesn't say how many, just says there need to be electrons in the d orbitals. So all you have to do really is which has occupied d orbitals in its ground state neutral atoms. Now, does that mean that the d orbitals are full? Well, let's take them one at a time. Maybe as we work through it, it'll be obvious. Barium, calcium, silicon, phosphorus, chlorine. Okay. Barium, where do we find barium? Barium is in first, second, third, fourth, fifth, sixth period, right? N equals 6. Can we have d orbitals there? Oh yeah, lots of d orbitals. Well, that one works. How about calcium? Calcium is in the 4th, but it's going to beyond that, we start filling d orbitals. We haven't got the d orbitals yet. Calcium's on the wrong side, right? So calcium can't be in. How about silicon? Silicon's N equals 3, right? Now, d orbitals are there, but they're not filled yet because silicon hadn't made it all the way over to argon and wrapped around toward the 3d orbitals. So silicon's not there. Phosphorus, well, it's right next door to silicon, same problem. And chlorine, and it's in the same row as these three. So the only one that has occupied d orbitals is barium. Now, trick question. 59. Of the following elements, which needs 3 electrons to complete its valence shell? All right. I should have left those up there. Looks like they're all the same. Barium, calcium, silicon, phosphorus, and chlorine. We need 3 elements to complete the valence shell. All right, so what's the valence shell for? Let's start with chlorine. It's a 3. N equals 3. In fact, it's got 3p. The highest, it's got a 3s2 and a 3p5. Right? 1, 2, 3, 4, 5. Count them over. So it only needs 1 electron. Right, so that's not it. Phosphorus. Phosphorus is 2s2, 2p3. Right? It needs 3, right? You can have a maximum of 6 in the p orbitals. So it needs 3. Okay, how about silicon? Silicon is 2s2, 2p2. It needs 4. Calcium. Well, calcium is 4s2 and no p's. So it needs 6 to complete the 4p. Barium. Barium is 1, 2, 3, 4, 5, 6. 6s2. It's the same boat as calcium. Right? It needs 6. The reason I put all these up here is so if I switch the question around and I say, how many of these need 6 electrons, and you can put 2. In this case, we're identifying which one needs 3 electrons, and that's phosphorus. Or which one needs 1 electron, chlorine. Okay. So it's not just a matter of memorizing the questions, it's understanding why the answers are the way they are. So then if something happens, if I get sneaky, then you can figure it out. Which of the following atoms has 3 electrons in p orbitals in its valence shell? All right, so if we're filling the p orbitals, we look at the right-hand side, right, in the p group, and we go 3 electrons in the p orbitals. We go 3 over. So the only ones that have 3 in there in that group are NP, arsenic, antimony, arsenic, yeah, antimony, and bismuth. I'm gonna stop there. So let's see, has 3 electrons, barium, gallium, vanadium, bismuth. Here it is. Bismuth has 3 electrons in its valence shell, and its p orbitals. Right, so bismuth would be 6p. 6p3 would be its highest energy level. Righty. Let's see, 66. Which of the following is the highest energy orbital for a silicon atom? Well, let's see. Where do we find silicon? Okay, it's in N equals 3, right? So 3s2 is full, and then we come over to silicon 3p2. So the following highest energy orbital is 3p. I think 67, yeah. Which of the following processes represents the ionization energy of bromine? Okay. This is, you can reason it out if you remember what I said about how to do it, or you can just memorize it. If we're going to do the ionization energy of bromine, we need the neutral atom of bromine, and it has to be in the gaseous state. Remember why? Because when you're ionizing bromine, you got to add energy to it. And if it's not a gas, you add energy to the liquid and make it a gas first. And that's energy that's not spent on raising the electron to infinity. So it has to be a gas first. And we add energy to it and we ionize it. Still a gas plus our free electron. So that would be C. Okay. We'll do 68. 68. Order the elements sulfur, chlorine, and fluorine. Increasing ionization energy. So the one that takes the most amount of energy would be to the far right. And that would be fluorine. It's the most electronegative element in the periodic table, which means it has the strongest pull on electrons, takes more energy. So this is the first ionization energy. If we don't qualify it by saying first, second, or third, just assume it's the first ionization energy. So fluorine is going to be on the far right, right? It's greater than these two. So how do they stack up? Well, sulfur is right next door to chlorine. And in a period, which they're in the same period, the one to the right has the higher ionization energy. So chlorine's next, and then sulfur. So that would be A. A would be that. Let's see, 69. Oh, we got the same ones again. I should have left them up there, I guess. Sulfur, chlorine, fluorine. Order the elements in terms of increasing atomic radius. All right. Fluorine. So what's the trend for atomic radius? It gets bigger from upper right to lower left, doesn't it? Right? They shrink as you go left to right, and they shrink as you go bottom to top. So the smallest one would be fluorine. So we're going to increase atomic radius. And these are neutral atoms. Right? So fluorine is going to be less than, what about sulfur and chlorine? Well, chlorine is going to be a little smaller than sulfur because they're positioned in the chart. So that should be D. Okay. Neutral atoms are fairly consistent in their trends as long as we stay in the representative elements. Once you get into the transition elements, things kind of roller coaster. That's why we stayed away from those. And then when you make ions out of them, it's even more difficult. Sometimes you just have to look them up in a reference manual to be sure. And then you have to be careful. How was the radius determined? I think there were 3 ways that we mentioned, or there was only 2. Um, 73. The following elements, which has the lowest first ionization energy? All right. So what are our choices? We've got barium, calcium, silicon, phosphorus, and fluorine. The lowest first ionization energy. Okay. The lowest would be the furthest to the left and the farthest down. So let's see. Chlorine's out. It's way up in the right-hand corner. Phosphorus is pretty close to it. Silicon is a little better. Calcium is better, but barium is below calcium. So barium's it. Barium has the lowest first ionization energy. Okay, we got another. Let's do 74, using the same ones. Okay, of the following elements, which is most likely to form a negative ion with charge 1 minus? 1 minus charge. All right. 1 minus. That would be a halogen, right? Halogen, right here. There you go. It only needs 1 electron to make it look like argon. All right, 75. Go. Which of the following atoms has the largest ionization energy? Okay. E. Let's see, we've got oxygen, lithium, neon, beryllium, acid. Actually, if you've got a noble gas in there, it's a pretty safe bet. It's got the largest ionization energy. Why? Because all of its electrons are core. Right? It's got completely filled orbitals, perfectly happy. It's not going to give up anything without a big push. So that's an easy one. If we took that one away, then we check the rest of them out. And the largest ionization energy would be, let's see, out of that group, see, oxygen's pretty good. Yeah, oxygen would be the best. Next to neon. $77. Wet whistle. Which has, Which has these types of electromagnetic radiation arranged in order of decreasing frequency? So decreasing frequency also means what? Mine's called blank. Lambda. Rainforests would be increasing. It's easier for me to think in terms of wavelength than in frequency. For some reason, the frequency just doesn't click with me. So if I know I need increasing wavelength, then I know that the one to the farthest right would be the greatest wavelength of all of them. Now, so what are our choices? We have visible, ultraviolet, and X-ray. Visible, ultraviolet, X-ray, what else? Radio. Infrared. X-ray, gamma. Gamma, that looks too much like. Do that better. Gamma rays and microwaves. Okay. So which has the longest wavelength? Radio is the longest. Do we have any with radio on the far right? No, we don't. What's the next one? The next one is microwaves. Do we have microwaves on the far right? Nope. Okay, the next one would be infrared, right? Infrared, is it on the far? There's one on the far right, infrared. Are they in the correct order though? Infrared, visible, and ultraviolet. Yep, that's it. So I took maybe what, 15 or 20 seconds to answer that question. And you can use that method, process of elimination. $78. Which has these types of electromagnetic radiation arranged in order of increasing wavelength? Well, it's the same thing. Right? Those two questions are exactly the same. The first one, 77, was worded in terms of frequency. This one's worded in terms of wavelength, and I solved the other one in terms of wavelength. So the answer is going to be exactly the same. See, 79. Which has these types of electromagnetic radiation arranged in order of decreasing energy? Okay, decreasing energy. Guess what? Decreasing energy, decreasing frequency. Yeah, do better than that. Increasing wavelength. Same answer. This is because of Planck's equation, right? Directly proportional. This gets bigger, that gets bigger. All right. I guess that was the point of doing those. 80. In the quantum theory, the magnetic orbital momentum quantum number is most directly associated with which property of orbitals? Well, let's see. That's the principal quantum number, L. This is not the magnetic. This is the angular momentum. Think. Yeah. And M sub L is the magnetic quantum number. And then, of course, you have the spin. Okay, so just for review, this one refers to energy and size. This one refers to shape. This one refers to orientation. And that was spin. Okay, so the magnetic quantum number is most directly associated with orientation. B. I thought I'd put them all up there, just kind of get things organized again in our brains. 81. So I'll leave that there for now. 81. In the quantum theory, the angular orbital momentum quantum number, this one, is most directly associated with which property? That's shape. D. Okay. And here we go. We're going to do another, going to do an electronic configuration for copper. And it looks like we have the opportunity to use our shorthand. 84. So copper has how many electrons in its neutral state? 29. Okay. Now, if we back up from copper, keep going back up to the third period, we end up at argon. And argon has 18 electrons. So now we only have to deal with 11 electrons. So how do we put them in there? Well, if we've got argon, then we move down to the fourth period to potassium. Now we're filling 4s. We got 2 of those. Then we're going to come across the 3d orbitals, and there should be 9 of those. This is one of the anomalies. Okay, we think it should be 4s2, 3d9. But remember, the Aufbau principle says electrons go into the lowest energy orbitals. And according to the quantum theory and the set of equations that govern the energy levels, the energy level for copper is going to be lower if we take one of these electrons and put it over here. Like that. The way things are set up, because these polyelectronic elements have complex interactions of their energy levels. Then the reason we make it 10 is it's more stable. Let's see, 1, 2, 3, 4, 5. It's more stable to have a complete d orbital than it is a complete s orbital. Okay, so that's why we do that, and that happens a lot. Well, it happens at certain points. Copper would be that way. Silver is probably that way too, and maybe gold. Okay. I have to look at let me just check it out. I think the one that I put in here in your review document has configurations in it. Yeah. Okay, so there's copper. And let's see, silver and gold. Yep. They do the same thing. For that explanation. Now, when you get to the point where you have 3D4, right, like this, like this, like this, like this, it's going to take a 4s and make it a 1 and put that electron here, because half-filled orbitals are also lower energy. Half-filled Ds are lower energy than fully filled S's. Okay. Yeah, I know it's strange, but Schrodinger's equations tell us that's the way it is.
It makes sense. It's just very odd.
Yeah, the way I deal with it is I go to this level, and then I look at the options and I say, oh, okay. So this one has to be moved over here to make it right. I don't just go automatically to that one. Or this one would be, let's see, this would be 5 then. Right. S1 D5 would be chromium. Yeah, chromium would work that way. And probably the other one's in chromium's group. Yeah, molybdenum. Now, tungsten doesn't do that. W. Only chromium and molybdenum do that. So other factors are involved, probably because tungsten also has filled f orbitals when you get to W over here. We've already gone through this row here, and now we've got a different situation with all those F's flying around. They must stabilize at the traditional levels. Okay. So the answer is B, 4s1 3d10. 85. Okay. Which of the following equations correctly represents the process involved in the electron affinity of X? So we're just picking any X. So we're going to start with a neutral again. It has to be a gas. Right? And instead of removing an electron, we're going to add an electron. So that gives us X minus gas. Okay. And when an electron falls from infinity to X, it gives up energy. So the enthalpy of this one is going to be negative. And the more negative it is, the more affinity that X has for electrons. Okay. So that's C. Let's see. Let's look at 86 now. Okay. Which of the following lists of atoms are arranged in order of decreasing atomic radius? Decreasing atomic radius. Let's see. What are our choices? Lithium, oxygen, nitrogen, fluorine, sodium, strontium. Oxygen's already up there. And fluorine, calcium, cesium, sulfur, and selenium. All right. We want decreasing atomic radius. So atomic radius decreases from left to right. Okay. And it decreases from bottom to top. Right? So we're decreasing from lower left, upper right, increasing from upper left to lower right. So if we want to go, what's the largest one in there? Right, that would be, let's see, cesium. Cesium is the largest. And then strontium is next. Yeah, strontium would be next largest. So this would be largest, second largest. Strontium. Calcium. Yep, calcium. Because they're in the same period as No, it's actually below that. Okay, that's good. Selenium might be next. Anybody above selenium? Sulfur. So let's say we have this one, and then sulfur is 5. And then sodium first. Sodium before sulfur. 6. Okay. And then we up to lithium, oxygen, nitrogen. Lithium then is 7, and then 8, and then 9, and then 10. That's probably the best order. So let's see which one fits. Lithium decreasing. Lithium, oxygen, that's out of order. Lithium, nitrogen, oxygen, fluorine. That's a good one. Lithium, nitrogen, oxygen, fluorine. I think we found our answer. Now that was the hard way to do it. You know, doing everybody and then picking it out. But we're pretty sure to get it right, even if they jumble them up. $86. Now watch 87. Oh, good. Afraid it was going to need those again. 87. 87. Consider an atom traveling at 1% speed of light. So the speed, the velocity equals 1% of c. The de Broglie wavelength is, the wavelength of this particle is 1.46 times 10 to the minus 3 picometers. Which element is this? All right. I wonder if we have enough information. What is 1% of the speed of light? 2.9979 times 10 to the 8th meters per second would be the speed of light. 1/10 of that would be the 7th, right? 7th meters per second. Okay. Wavelength. If we need to use wavelength in a formula, it's going to have to be meters. So what's a pico? Let's see. Micro is -3. Micro, no, -6. Milli is -3. Micro is -6.
Pico's -12.
Yeah, pico's -12. What's -9? Nano. Yeah, nano, and pico is -12. 10 to the -12. Yep. So what we have here is a wavelength of 1.46 times 10 to the -15 meters. Okay. Now, what do we need to determine what element it is? We either need to know the atomic number of protons, which we can't get from that, I don't think, or the molar mass. Right, the molar mass would be it. Right, so the molar mass is equal to the mass of so many moles. Let me see, so that I don't waste a bunch of time. Let me refresh my memory. I'm good up to that point. Okay. All right. So actually, I'm going to combine two equations. Okay. The one that has mass in it is Einstein's equation. The one that relates wavelength is I'm having trouble today. I just said it a few minutes ago. Yeah. But we've got wavelength. Right. So what we need is speed of light equals times that. So if we substitute in here, that one is going to be Planck's constant times c over wavelength. But we don't have the speed of light. We have the velocity of the particle. So wherever we have the speed of light, we have to substitute the velocity of the particle because it's not moving that fast. Okay. So for this one, we would say, let's see, is that right? Let me check myself. Yeah. So I'm going to take this equation and this one and put them together. Oops. And this one needs to be B. So let's see, where do they cross? Well, they're both equal to E. So we could say mv squared equals hv over lambda. And if we solve for mass, that puts hv over v squared lambda, correct? So the v's cancel there and leaves us with one there. So we've got Planck's constant divided by v times lambda. That'll give us the mass of the particle, the mass of the atom. Okay, so we need Planck's constant, 6.626, is it? Yeah, times 10 to the minus 34. For joule seconds divided by the velocity, which is 2.9979 times 10 to the 7th meters per second times the wavelength, 1.46 times 10 minus 15 meters. Let's see if I get the same answer as that one. 6.626 exponent 34 2.9979 exponent 7 divide 1.46 exponent 15 change the sign. So I get, okay, we're going to get a value because this is in SI units. The mass is going to be in kilograms. 514 times 10 to the minus 26 kilograms. So how many grams is that? Well, kilo is 10 to the third. Right. So 10 to the third plus minus 26, 10 to the minus 23. 1.514 times 10 to the minus 23 grams. Well, now we have grams. We need to know how many moles. I do believe. Well, that's grams per atom. Oops. I make a mistake in calculations. I think I did. 1 second. 1% of the speed of light is not 10�7, it's 1/100th. Right? 1% is 1 part per 100. That should be 6. Okay. Nobody caught me. Okay, so that goes right in here. We're dividing by 1 less. 25. This is 22. There we go. So that's the mass. Actually, that's the mass of 1 atom. Right? Because we say 1 atom is moving at that speed and has this wavelength. That's the mass per atom. So we can take this value, 1.514 times 10 to the minus 22 grams per atom. Now we need the number of moles. That many grams per mole. Like we know 6.022 times 10 to the 23rd atoms per mole. So we just have to multiply that value. Let's see. I'll just put it in again. 1.514 times 6.022 exponent 23rd. Okay. So this, round off the 3 places, is 91.2 grams per mole. Now we go to our periodic table. 91. Zirconium, I think, is the closest one. See, if I'd have kept going, I'd probably ended up with 9 grams per mole. Right. And beryllium is up there. So if I'd have done it wrong, I'd have said beryllium with my values. Say, uh-oh, that's wrong. That looks like an extra credit question there. You can spend, what did I spend? 15 minutes on it at least. That's precious time in an exam. 88. In an investigation of electronic absorption spectra of a particular element, it's found that a photon having wavelength 500 nanometers provides just enough energy to promote an electron from the 2nd quantum level to the 3rd. So it goes, this is just enough energy to go from N2, 2nd level, to N3. Yeah, from this information we can deduce what? Okay, we're not going to actually have to do a lot of calculations for this one. We just need to know qualitatively what's happened here. This amount of energy came in and promoted that electron from this energy level to that energy level. There's 1, there's 2, there's 3. Right, so it went like that from those 2 levels. So the energy of the N equals 2 level. The energy of the Oh, what can we deduce? Can we deduce the energy of the N equals 2 level? It's kind of hard. Because we don't know that this is a hydrogen-like atom, so we can't use that energy calculation. Remember the formula? Well, remember seeing the formula? If it's not hydrogen-like, then we can't say what the energy is. We can't do that for level 3 either. We can't tell the sum of the 2 energies because that doesn't matter. The energy we want is the difference between the 2. The difference in energies between N2 and N3. We should be able to do that one. Well, that's the best answer. Actually, it's not a good answer because it doesn't say this is hydrogen-like, does it? No, it doesn't. Right. So we need more information to actually deduce what the energy level is actually. But this information, yeah, we can. Yeah, we can. We can do that. We can't tell what the energy is for 2 or 3, but we can tell what the energy is for the difference because that's exactly the amount of energy it took to go from here to here, right? It came in like that, right? We just have to calculate H nu or HC over lambda, and we can do energy. Right? We just convert this to meters, put it in there, put the speed of light in there, put Planck's constant in there. We can calculate the energy transition from 2 to 3. Right? We can do that. So D is the best answer. My original problem with A and B stands. We can't actually calculate the energy of 2 and 3 because we don't know if it's hydrogen-like. If it is hydrogen-like, then we could go ahead with it. But this information tells us that's the amount of energy required for this promotion, and we can calculate the energy from Planck's equation. Because Planck came up with this equation before Bohr's model. Right? He proved this one before Bohr even gave us his planetary model and the equations that go along with it. So this equation stands on its own. It doesn't need the Bohr model to tell us anymore. Okay. Consider the following portion of the energy level diagram for hydrogen for the next 2 questions. Okay. So there we have the actual energy values for n equals 1, 2, 3, 4, 5, all calculated out for you. You don't have to use that equation to answer 89 and 90. So we're coming up on 1:45. That means we have lab left over to finish. In the hydrogen spectrum, what's the wavelength of light associated with n equals 3 to n equals 1 electron transition? So we're going from N3 to N1. Be consistent, babe. N1. So we're coming from 3 down to 1. That means we're going to give up energy. Right, we're going to lose energy. That means our value should be negative. So what we do is we say, if we're going from N3 to N1, what's the energy for 3? No, it's final minus initial. It's the energy of 1 minus the energy of 3. Right? Final position is 1, initial is 3. So it's 1 minus 3. Okay. So 1 is minus 2.178 times 10 to the minus 18 joules. And then we subtract a minus 3.2420 minus 0.2420 times 10 plus 17. Okay, so this becomes positive, and we just add a positive to a negative. 2.178, change that sign. I don't even have to do these until the end, because we're only interested in the coefficients, since the powers of 10 are the same. 2.42. Okay, so this is minus 2. No, that's not right. Let me do that again. 2.1. There we go, that's better. Minus 1.936 times 10 to the minus 18 joules is the energy transition. Oh, it left the sign off, didn't it? Rounded off 1.94. Why does it say E? Did I subtract the wrong ones? Maybe I got the wrong answer up there. Oh. Huh. Now, why does it do initial minus final? Oh, I'm not done yet. The question is, what's the wavelength? Not just the energy, what's the wavelength? And we're not going to use a negative sign in the wavelength. We only need the amount of energy. It works both ways. Energy absorbed or energy released doesn't matter. So now we want to calculate the wavelength from that energy. So we're going to use Planck's equation, hc over lambda. So the energy is equal to 1.936 times 10 to the minus 18 joules equals Planck's constant 6.626. Is it times 10 to the minus 34? Yeah. 10 to the minus 34. I'm getting bunched up here. I'll tell you what. Let's solve it for lambda. Right, lambda in the denominator here, lambda in the numerator here. And then E goes over here. So it's HC over E. That's better. Now we can put Planck's constant, 26 times 10 to the minus 34 joule seconds times the speed of light, 2.9979 times 10 to the 8th meters per second, divided by the energy, 1.936 times 10 to the minus 18 joules. Okay. Now that'll give us the wavelength in meters. Let's see, change that sign. And then 2.9979 exponent 8 divide. And that's times 6.626. 34. So I get 1.03 times 10 to the minus 25 meters. Oops. I did something wrong. 6.626. Did do something wrong. Minus 7. There we go. And it looked right. That'd be an awful short wavelength. I don't think we got that much energy. Okay, 90. That would be E. 90. What's the wavelength of light that is emitted when an excited electron in the hydrogen atom falls from n equals 5 to n equals 1? Okay, so now we're going 5 to n equals 1. Let's see. Can we go back up and use that next two questions? Yes. Right? Yeah. So we can go n equals 5 to n equals 1. How much energy, what's the wavelength of the light? So we got to go energy first from 5 to 1. So it really doesn't matter whether it's the proper order or not, but just to be consistent, minus 2.178. The final minus 2.178 times 10 to the minus 18 minus a minus 1 is minus 5. 0.08712. 0.08712 times 10 to the minus 18. Notice where this is not scientific notation, and we're doing that so that we can keep the exponents the same. That way we only have to deal with this part of the number, the coefficient. So 2.178, change the sign, and then 0.08712 plus. So I get 2.091 times 10 to the minus 18 joules. That's the energy transition. Actually, it's a negative because when it drops from 5 to 1, it's giving up energy. But for our calculation purposes, we only need the absolute value. So we're just going to take the absolute value of that and go back to our old equation, which I'm going to have to redo. That's HC lambda. So we're looking for lambda. Lambda comes over here. HC are over here, and E's on the bottom. Now we can do 6.626 times 10 to the minus 34 joule seconds for Planck's constant. Speed of light 2.9979 times 10 to the 8th meters per second. And then energy is 2.091 times 10 to the minus 18th joules. Joules cancel here, seconds cancel here, leaves us with meters. That's good. Now let's see if I can operate the calculator, because that's the thinking part. The rest is number crunching. Eight. 091. It's going minus 18. So I get 9.4998 times 10 to the minus 8 meters. Is it in meters? Yeah. So round it off 9.50. That's B. All right. And 91 stands on its own. Which of the following is a reasonable criticism of Bohr model of the atom? Okay. It makes no attempt to explain why the negative electron does not eventually fall into the positive nucleus. Makes no attempt to explain why the negative electron does not eventually fall into it. No, it doesn't. It doesn't make any attempt to explain why the negative electron doesn't fall into the positive nucleus. All right, so A is a possibility. How about B? It does not actually predict the line spectrum of hydrogen. That's wrong. It does that very well. C, it does not adequately predict the ionization energy of the valence electrons for electrons other than hydrogen. That's true. Yeah, that's true. It can't go beyond. It can't talk about any kind of energy transition except for hydrogen-like elements. So C is good too. Actually, C is better. It does not adequately predict the ionization energy of the first energy level electron for one electron species. Yeah, it does. It does that very well. It shows electrons to exist outside of the nucleus. Oh yeah, yeah, it does. Right, it's like planets, right? So, If that one shows up on the exam, I probably have to accept A or C. If I put that exact question up there, you know, if I correct it so that it's written properly, then one or the other of those would be the ideal. I don't know, maybe Bohr did try to explain why negative electrons don't fall into a positive nucleus. Maybe they have so much momentum, they stay in orbit. I don't know. But at this level, I'd have to accept both of them. Which of the following statements is or true? Okay. So let's take a look at 93. An excited atom, this is Roman numeral 1. An excited atom can return to its ground state by absorbing electromagnetic radiation. That's the other way around, right? It gives up energy when it does that. The energy of an atom is increased when electromagnetic radiation is emitted from it. That's the same way as saying 1. The energy of electromagnetic radiation increases as its frequency increases. Yeah, that's true, right? Because we know this. As its frequency increases, its energy increases. So Roman numeral 3 is good. 4, an electron in the n=4 state in hydrogen atom can go to the n=2 state by emitting electromagnetic radiation at the appropriate frequency. Oh, yeah. Right. That's true. The frequency and wavelength of electromagnetic radiation are inversely proportional to each other. The frequency and the wavelength are inversely proportional. Is that true? Yeah. Speed of light equals lambda times. Yeah. Yeah. 3, 4, and 5. Let's see which one. D. All right. 94. Consider the following representation of a 2p orbital. Okay. I usually do it like this. There's X, there's Y, there's Z. And say we're going to put a p orbital on the y-axis. So it goes like that. Like that. Which of the following statement best describes the movement of electrons in a p orbital? In the p orbital. The electrons move along the outer surface of the p orbital similar to a figure 8. That's funny. It's not true either. The electrons move within the 2 lobes of the p orbital, but never beyond the outside surface of the orbital. That's not true either. Why? Because this shape is based upon probability. They can exist outside that shape. They can exist inside that shape. We don't expect them to exist to any great degree out here, or even right here, because that's a node, 0 energy. But they can be outside that shape. Remember Heisenberg's principle, right? We're more interested in their energies rather than their positions. This sort of gives us a rough estimate of where they'll be. The energy is more important. C, electrons are concentrated at the center node of the 2 lobes. No, the node means 0 probability. Yeah. How about D? The electrons are only moving in 1 lobe at any given time. No. They can be anywhere. We don't know where they are. That's why we have that shape. That just kind of localizes them as best we can. We don't even know where they are. The electron movement cannot be exactly determined. That's the best answer. You don't know how they're moving. In fact, even though we can treat electrons as particles, in orbitals, they tend to behave more like waves. So if we drew a hydrogen atom with 1 proton and 1 electron, saying it's ground state, right? N=1. The best way to represent that electron is with a wave. That perfectly, well, that's not perfectly, has wavelengths that perfectly meet all the way around. That's one of the explanations for why only certain energy levels can be occupied, because anything in between will have the wrong wavelengths. They'll come along and they won't meet. Their tail and head and tail won't meet. Right? They'll be offset, and that can't happen, right? Unless you draw it wrong. Okay, that was just a teaser. But Schrodinger's equations were based upon wave theory for the electrons. So that's probably his approach. Okay. But I'm not well versed enough in quantum mechanics to explain it any better. How many electrons can be contained in all the orbitals with n equals 4? All right, n equals 4. We could have L equals what? 0, 1, 2, 3. M sub L. Okay. M sub L for this one can have 1. I can have 0. Right? For this one, we can have -1, 0, +1. For 2, we can have -2, -1, 0, +1, +2. And for 3, we can have -3, -2, -1, 0, +1, +2, and +3. Okay. To say how many electrons? Yes. So M sub S means 2 times that many. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16. So that would be 32, right? 32 electrons. Yeah, that's right. 32 electrons, E. That's doing it the long hand way. If you know how many are each one, like this can have 1, this can have 3, this can have 5, this can have 7, then you can just add them up times 2. But if you want to be absolutely sure, just draw them out and count them up. That was 95. My goodness, it's like I've highlighted every one in the book. 96. Small but important energy. Let me see. Yeah, I should have checked earlier. Kathy's with us. Let's see. Did Alexis ever show up? Alexis Curry. No, unless I missed her. All right, 96. The small but important energy difference between 3s, 3p, and 3d orbitals are due mainly to the small energy differences between 3s, 3p, and 3d are due mainly to the number of electrons they can hold. Yeah, I don't think so. Principal quantum numbers? No, it can't be principal because they're all the same. Right? So we can't blame it on principal quantum numbers. Heisenberg uncertainty principle? That doesn't say anything about energy levels. It just probabilities of momentum versus position. So it has Heisenberg has nothing to do with that. The penetration effect. Penetration effect accounts for the overall energy differences between them. Because The 3s has 2 nodes and 3 humps. And one of the humps comes closer to the nucleus than 3p and 3d. Remember that picture? It's kind of like this. It goes, let's see, 3. 0, it goes up. So that would be 3s. 3p doesn't penetrate this far. Like 3p is only maybe like this. Like that, I think. And then 3d even goes over here. Actually, 3d is just one hump. Because it's the first D. And so it just is just like this. And so 3s penetrates here, 3p penetrates here, and 3d doesn't penetrate at all. Okay. I don't know what else to say. Yes, there it is. '97. Which of the following was not an elemental property usually predicted by Mendeleev for as yet unknown elements? Okay. Mendeleev had no idea about electronic configurations and didn't have a clue. He was way before that. Right. So we actually found our answer. He did predict atomic mass. He did predict densities, boiling points, oxide formulas. In those days, knowing the oxide of an element was, I mean, it was like the pot of gold at the end of the rainbow. Right? Everything was oxides. And most everything in the Earth's crust is oxides, right? All the metals anyway, except for gold, right? Sometimes you can find silver, free nuggets of silver, but it's very rare. Gold is more likely. Okay. So A is the answer. Mendeleev had no clue about electronic configuration. He was basing upon these other factors to group elements. Okay, 98. Which of the following atoms or ions has 3 unpaired electrons? Okay, what are our choices? Nitrogen, oxygen, aluminum, sulfur 2-, and titanium 2+. All right, 3 unpaired electrons. What you want to do here is look at the very highest orbital, because that's where they're going to be. So what's the highest one for nitrogen? Well, nitrogen is going to be 2p. And it has 7 electrons. I guess we have to look at them going up to that point. So 1s2, 2s2, 2p, 3. Well, they're going to be unpaired, aren't they? I think we found our answer. Yeah. Save time on a test. Once you find the right answer, you move on. But that's the process we would do. We'd fill them in and look at the highest orbital and see the highest subshell and then its orbitals and put the electrons that belong to that subshell into the orbitals using Hund's rule. (101). An element E has the electron configuration krypton, which is 36, and it's 5s2, 4d10, and 5p2. Is that even possible? The formula for the Oh yeah, D can have 10. I was off in F orbital land. Yeah, that's possible. Okay, so the formula for the fluoride of E is most likely. So you look at the valence electrons, you've got 2 here and 2 here. Right? So when E becomes charged, it can either be 2 plus or 4 plus. If you lose these two, it'll be 2 plus. If you lose these two also, then it'll be 4 plus. Those are your possibilities. Okay. Did I lose somebody? I guess technically you could lose one of these, then you could lose the other one, and then you could lose one of these and the other one. So you could have, I don't know, 1, 2, 3, and 4 possible. But what's most likely out of those choices? Most likely, and it's most stable if you lose all of these or all of those and all of these. Okay, so these are the best choices, 4 plus or 2 plus. If it's 2 plus, then you can have 2 fluorines because they're 1 minus. Or if it's 4 plus, you can have E4, EF4. Right, so that's why B is probably the best answer. Which element would that be? Let's see. 5p. 1, 2, 3, 4, 5. Got to be 10. That would be 10. And let's look. I'm curious. Our periodic table gives us the most likely ions. 2 and 4. Yep. That's why the most common ions for 10 are 2 plus and 4 plus. All right. We ought to be getting close. 104. Which of the following atoms would have the largest second ionization energy? Aha. Okay, magnesium, chlorine, sulfur, calcium, sodium. All right. Look at the valence electrons available for ionization. For magnesium, it's just 3s2. Chlorine is 3p5. Sulfur is 3p4. Calcium is 4s2. And sodium is 3s1. Okay. What I would look for is, if we're looking for the second ionization energy, look for the one, we remove 1 electron from each one of these, what does that give you? So move electron here, that gives us 3s1, right? We've still got a valence electron available. This would be 3p4, definitely got electrons available. 3p3, 4s1. This one actually goes back to 2p8. No, 2p6, excuse me, 2p6. So once you get rid of this one, you're back to 2p6. That's a core. You're getting down into the core. These, you still have valence left. This one, you're into the core. Its energy is going to be 10 times as much as the first ionization. So sodium's the best answer. Let's see. Just keep coming and coming. 107. Which of the following concerning second ionization energies is true? Okay. That of aluminum is higher than that of magnesium. Is that true? Aluminum's second ionization energy for aluminum is greater than second ionization energy for magnesium. Probably. Yeah, probably. Because aluminum has 3 valence electrons coming from 2s2, 2p1, and this one is 2s2. So this is from a higher energy orbital. So no, the second ionization energy, no, it won't be. No, it should be less than. Right, so that's wrong. I mean, that first statement, the first part of the statement is wrong. How about that? Aluminum is higher than that of magnesium. All right, they're saying it's higher because the electrons are taken from the same energy level, but the aluminum atom has 1 more proton. That's true. Right. If you go from left to right, the first ionization energy should be higher for aluminum. So, okay. All right. If the first ionization energy is higher for aluminum, the second ionization energy should also be higher for aluminum, because we're still not into the core. Okay. And aluminum has 1 extra proton. So that B is the best answer, I think. They're still definitely not equal. Okay. Any questions? I don't think I explained that very well. Okay, we're going to move on. 108. Okay, consider a planet where the temperature is so high that the ground state of an electron in the hydrogen atom is n equals 4. Right. I made a side remark to that effect earlier. Ground state on this planet is n equals 4 because it's a lot hotter. Can't get any lower than 4. What's the ratio of ionization energy for the hydrogen in this planet compared to that on Earth? All right. So we need the ratio of the first ionization energy. Well, ionization energy for hydrogen, there's only 1. Or ratio on this planet, on the exoplanet, compared to the ionization energy on Earth. Okay. So what would be the ionization energy for the first ionization energy? What we would need is a difference in energy from going from n to infinity. Energy 4 to energy infinity. And for Earth, it would be energy 1 to energy infinity. Okay. All right. So if we go back to the oh, geez, so I don't wander around. If we go back to the calculations of what would be the ionization energy for this one? Well, it would be the energy of infinity minus the energy of 4. Right, final minus initial. This one would be the energy of infinity minus the energy of 1. Okay. Okay. So let's come down here. What's the energy of infinity? Right, the energy of infinity is minus 2.178 times 10 to the minus 18 joules times z squared, which in our case, hydrogen would be 1 squared, okay, over infinity squared. Right, because that's n is equal to infinity here. And then we would subtract the energy of the fourth level, which would be minus 2.178 times 10 to the minus 18 times 1 squared over 4 squared. And so this is n squared there. And that would be divided by this same value, exactly the same, right? It's the energy of infinity minus the one for Earth, 10 to the minus 18. This would be 1 squared over 1 squared. Okay. All right. So we can get rid of this. Is going to be positive, positive, right? Positive, positive. That goes away. Well, because these are both 0, right? 1 divided by infinity is 0, correct? So 0 times that is 0. 0, 0. So we can factor these out. We can factor this one, right? Since they're times here, times. This one times that one, this one times that one is this one divided by that one times this one divided by that one. So this one divided by that one is 1. Okay. The question now is, what's this one? Well, this one is 1 over 16 divided by 1 over 1. Okay. So what's that? Well, this is 1 divided into that. It's 1 to 16. So that ratio is 1 to 16. Not 16 to 1, 1 to 16. The amount, and it makes sense. The ratio takes less energy on the exoplanet because the electron's already at level 4. Whereas on Earth, it's at level 1, we got to add more energy. So the ratio of the two should be the smaller on the top, larger on the bottom. That's how I check myself to be sure I did it right. Okay. That was 108. And how we doing? Okay, skipping a bunch. I'll spring one on me. Well, lots of repetition. That's it. Yeah, that's it.